Okay, we're ready to talk about the inclusion-exclusion identity, which we're going to build it up by starting with two sets, looking then at 3 and 4, and seeing if we can generalize. So if we want to look at the probability of E union F, we have, this is the probability of E plus the probability of F minus the probability of their intersection, right? So we can see this visually with Venn diagrams. So if that's E and that's F, we add the probability of E, so we get this whole circle. We add the probability of F, we get this whole circle, and we see that we have counted that interior part twice, so we subtract off one intersection. And that should give us the probability of E union F without the overcount. All right, so how then do we extend this idea to the union of 3 sets? Let's go back to black. All right. So if we want to look at the probability of E union F union G, well, again, if we draw this with Venn diagrams, we can see perhaps what's getting overcounted, okay? So I'm going to draw it. First of all, let's just start with adding them all up. The probability of E plus the probability of F plus the probability of G. Right, so we have that, and we have that. Now, we know this outside stuff is getting added. So when we do the probability of E, we get, here I'm going to try to keep it so we'll say this is E. We will get this, this, and this, as well as this over here. I just don't want to cloud up our picture, so you'll see. If I then do the probability of F, I will get all that over there, but I'll also get this, this, and that. And then if I do the probability of G, I'm going to get, of course, that, this, this, and that. And so what I really want to illustrate here is these pieces, these little outside pieces of what looks like that football, those are getting double counted, whereas this thing in the very center is getting counted 3 times. Okay, so let's see what happens if we kind of apply what we did above and we subtract off the intersection of E and F. So that means we get rid of one of the, so let's look at, maybe we get rid of the green and we're left with just the blue here, right? I don't think I can draw that without messing up the whole picture. Hold on, yeah. It's too small for me to do it. Okay, that's fine. And then if we subtract off minus the probability of FG, we subtract off one of the pieces in this outside plus one in the middle. And then if we again subtract off E and G, we get rid of one of them out there and then one in the middle. And that means we get rid of that interior piece, which is getting subtracted every time we subtract these pairs 3 times. So we don't have anything in that very center now, right? And so we actually now need to come back and add the intersection of all 3. Because we took off the extra count that we wanted with EF, FG, and EG, but we also took off the intersection of all 3 every single time, and now we're left with none. Okay? Well, so this actually is what is the probability of E union F union G, and we could even show this analytically. Okay, so we're going to do a little bit of set theory here. And let's construct our left. So what we're going to do is we're going to take E union F union G, and we're going to rewrite it as the union of 2 sets, right? So this is going to be, we'll say E union F union G. Okay, so you could think of this set right here as like its own set, and now you're really looking at the probability of A union G. right? And then we fall back to what we claimed in the beginning. How do we apply this identity to the union of two sets? And so this becomes the probability of that first set, which is E union F, plus the probability of the second one, G, minus the probability of the intersection of those two sets, which is E union G. I'm going to put them in parentheses. I'm sorry. That should be E union F. Hold on. E union F intersect G, right? That's like A plus G, A intersect G. All right? Now, we know what we can do with this one. We can apply the property that we showed above, okay? But what we wanted, the new player here is this right here. And so now we're going to pull in a little bit of set theory that hopefully you know from previous classes. But if you want to take G, or you take this union of these two sets intersect G, that you can distribute the intersection over that union. Okay, so this thing right here actually becomes the probability of E intersect G union F intersect G. That's what that's what happens when you distribute the intersection over the union. Okay, so there's a minus there. This comes down and is the probability of G. And in this one, we apply the principle the first time, and we get the probability of E plus the probability of F. Let's see if I can fit it in there, minus the probability of E intersect F plus the probability of G. All right, so this piece right here comes from that. The G comes down, and then we translate this. Okay, guess what we're going to do here? We're going to apply that first identity to the union of these two sets. So let me just rewrite this. Probability of E plus the probability of F. I'm going to move that G over because we know that's what we're going to want. And then minus the probability of EF. Okay, minus. Now I'm going to put this back in parentheses so I don't mess up my negative. And I'm going to apply that principle, and I get the probability of EG plus the probability of FG minus the probability of the intersection of those two sets, which is E, G, F, G. Okay? Now, intersecting E, G, E, well, G with G is just G, so this really is the probability of E, F, G. Okay? It's just throwing in intersecting with G again doesn't change anything. Okay, so now let's distribute our negative, and we see we get, we'll do it all in blue, probability of E plus the probability of F plus the probability of G minus the probability of EF minus the probability of EG, distribute that negative, minus the probability of FG minus plus the probability of EFG. So it's exactly what we said up there, right? We add them all up, E, F, and G, and then we subtract all their intersections, but we realized when we did that, we took out that third one 3 times, so we put it back in. Okay? So we can show this using some set theory, as we also showed with our Venn diagram there. But the question is how do we extend this to beyond 3? Because our Venn diagram is going to fall apart very quickly after 3. Okay? Well, based on this pattern here, let's see if we can make a guess of what we think would happen if we unioned up 4 sets. So let's now, because I'm going to run out of letters, obviously not at 4, but I'm going to say this. We'll look at the probability of E1 union E2 union E3 union E4. Okay? Now, if we were going to go through our reasoning that we did above, it would be perhaps reasonable to assume that we'll get plus the probability of E2 plus the probability of E3 plus the probability of E4. Now, we know we've done lots of overcount. So if you can imagine those little footballs, although the Venn diagram for 4 is not very visually helpful, but if we subtract off all those pairs of intersections, so we get E1, E2 minus E1, E3 minus E1, E4 minus E2, E3. We don't want to count E2, E3, E3, E2 differently, right? So we gotta have some systematic way of doing this. E2, E4, and then lastly, E3, E4. Now the question is how many intersections did we have here that we actually had to subtract, right? Well, we had 4 different sets, and what we have here is, I think 6, right? 6 sets of intersections. Really what we had is, of the 4, choose the pairs, and 4 choose 2 is 6. So we had 6 pairs of intersections. Okay, we probably took all those intersections. We probably need to put stuff back, but not just one intersection. This time we have lots of intersections of groups of 3, right? So now let's look at our groups of 3 and let's add back. So E1, E2, E3 plus, let's be careful. Oops, I've got my P there. Plus, we'll say E1, E2, E4, right? Yeah, plus E1, E3, E4, I think I got them there. Now let's move to the 2s, E2, E3, E4. Yes. So I'm adding those back up. And the question is how many triples do I have? Well, it's really taking the 4 sets and grabbing groups of 3, of which there should be 4. Okay, but we've now added back too much this time. So we are going to take away, I know we can't see it with a Venn diagram, but we're going to now subtract off the intersection of all. And in fact, you can show this by creating this as either the union of 2 sets or the union of 3 sets, apply above, and apply what we did with 3 sets, and you'll eventually get down to a piece that involves 2 sets, and you can show that this is true for 4 sets. Okay? That's certainly not a proof, but at least it leads you down here. But I feel like what we are now ready to do is to write it formally in terms of n sets. Okay, let's do that. So let's change this so we have, we'll do in red. That's a good color. Okay, so if we're going to look at the probability of E1 union E2 union all the way up to E sub n sets, then based on this pattern that we've been constructing, we will first sum up all of the sets individually. So I equals 1 up to n minus, now here we have to be careful. So make sure you understand the notation that we're using here. We're going to sum up all the pairs, okay? So we have to have a way to index these, right? So I'm going to say E sub I1, E sub I2, but I'm going to make it such that I1 is less than I2. Okay, that way, so remember when we did it up here, we made sure that we did E1, E2, and we didn't do E2, E1, right? We did E1, E3, but we didn't do E3, E1. So setting it up this way makes sure that we don't overcount, or at least in this notation, overcounting the pairs. Okay? So we're going to sum up all of those, and then we're going to add and so forth. And our signs are going to alternate. So we're going to say -1 and we're going to put a power here, and then we'll figure out that pattern again down the road. So we're going to do, let's just pick, so here when it was 2 sets, right, we subtracted off the intersection, right, and then we're going to take, actually, let me rewrite this one step better, okay? So let's just do the third one, just for everybody to be clear before I tack on that last one. Oops, back to red. Okay, so the next one would be, oops, sorry. This is a new app, and so I'm not quite adept at it yet. Okay, so now we're going to add up all the triples. So this is why we have the I sub 1, I sub 2, I sub 3, because this could keep going past the alphabet. So we don't use ij, we'll use I sub 1, I sub 2, and so forth. So here it would be adding back I sub 1, I sub 1, I sub 2, right? E sub I sub 3. And we're going to put that restriction that I sub 1 is less than I sub 2 is less than I sub 3. That keeps us from overcounting that order. So we're just always going to order them, whichever 3 we grab, smallest to largest. Okay? The next thing we would do at this stage would be to subtract, add, subtract, add, subtract. So here, dot, dot, dot. And the question is what happens in this last step, right? Well, when we had 2 sets, we subtracted off the intersection. When we had 3 sets, our last step was to add on the intersection, right? There was our adding on. When we had 2, we subtracted. When we had 4, we subtracted. So it really depends on whether our number of sets up to n are even or odd, right? So we'll say when we want it to be negative if n is even, right? So we'll make that n minus 1 or n plus 1. Probability of E1, E2, dot, 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 E sub n, the intersection of all n of them, okay? And this right here is the inclusion-exclusion identity that will come in handy for us in specific problems that I'll illustrate in another video.